Okay, so in this video, we will try and determine whether the series converges or diverges. And as we're about to see, this series is more interesting than it looks. So we're summing the terms from 1 to infinity, sine of n over n squared. So this is of course a n, the sequence we're trying to sum over. And to get a feeling for what we're summing, let's write the first few terms of this infinite series. So when n is 1, we have sine of 1 over 1, which is just sine of 1. When n is 2, we have sine of 2 over 2 squared, which is 4. When n is 3, sine of 3 over 3 squared, which is 9. Plus when n is 4, we have sine of 4 over 4 squared, which is 16, and so forth. So let's see. Let's go over every test we have developed so far and see if any such test applies. The first test was the divergence test. If the terms we're summing over do not converge to 0 as n tends to infinity, the terms are too big, the series will diverge. Well, sine of n as n goes to infinity will oscillate forever between -1 and +1, and n squared goes to infinity. So as this is bounded by 1 over something which blows up to infinity, this will clearly shrink to 0. So the divergence test fails. Then look at all of our other tests after that. We had looked at geometric series. This is clearly not a geometric series. We looked at p-series, close to but not a p-series, as we don't have 1 over n squared but sine of n. So this is not a geometric series, not a p-series, that's out. Now look at the following three tests. The integral test, the comparison test, and the limit comparison test. All three tests require that we are summing terms of a sequence where the terms are positive. Is that the case here? And the answer is no. Sine of 1 is positive, sine of 2 is positive, sine of 3 is positive, sine of 4 is negative, and so forth, right? Think of n being a discrete argument going around the unit circle, and as n goes to infinity, you will go around the full circle, the unit circle, an infinite number of times, and so sine will be infinitely often positive, infinitely often negative. So because we have this infinite set in our sequence of positive and negative real numbers, we cannot use the comparison test, the limit comparison test, and the integral test, all out the window. So the only test we are left with is the alternating series test. So here, if you look at this, well, we do have an alternation in sign, right? Sine of 1 is positive, sine of 2 is positive, sine of 3 is positive, then sine of 4 is negative. Sine of 5 is negative, sine of 6 is negative, sine of 7 becomes now positive, as 7 is slightly larger than 2 pi. But the problem is, this is not an alternating series. An alternating series requires a systematic alternation between positive, positive, negative forever. After every positive must be a negative, after every negative must be a positive. This is clearly not the case here. So the alternating series test fails. It may not be applied. So every test we have developed up to now fails miserably. Well, now what? If we go back to something we've said before, this is really close to a p-series, right? Sine of n over n squared. If you think of it, sine of n is never larger than 1, so we might want to compare sine of n over n squared to 1 over n squared, and then use some type of comparison test. The only problem is the comparison test can only be applied when you have a series of terms and the terms are all positive. So how can we go around this problem? Well, the idea is, let's make this positive. Let's take the absolute value. Whatever the sign of an is, whether positive or negative, the absolute value of anything is always non-negative. Well, this is the absolute value of sine of n over n squared, which is the absolute value of sine of n over n squared. As n squared is always positive, I can drop the absolute value. And now, no matter what the value of n is, sine of n is never larger in absolute value than 1. So I can bound this above by 1 over n squared. And now this should be interesting. We are saying that for any n, the terms a n in absolute value are non-negative, this is obvious, and also no larger than 1 over n squared. So, if we sum the smaller terms, this will be clearly no larger than summing up the larger terms. And now this is a simple p-series where p equals 2, and 2 is strictly larger than 1. So not only do we have here p-series, but this p-series converges as p is larger than 1. So this p-series converges, therefore is a real number, therefore is less than infinity. It's finite. And now think of it, we can use the comparison test. The terms a n in absolute values are non-negative, so we have here a sum of non-negative terms. And so as we sum more and more of these terms, the sum gets larger and larger and larger. So this gives us an increasing sequence of partial sums, but it is bounded. It is no larger than this real number. So here, the series is finite. And when we have a series of positive terms, or at least non-negative, as we have just said, as we add more and more terms, the sum gets larger and larger and larger, so we have an increasing sequence of partial sums. That increasing sequence is bounded, therefore is finite, so this converges by the monotone convergence theorem, or simply by the comparison test. We have two sequences, the smaller sequence, the larger sequence. So if we sum the smaller terms, it's no bigger than summing the larger terms, because this sum is finite, so is this sum, therefore this series converges by the comparison test. And an, if you recall, was simply sine of n over n squared. You could of course just written CT. So it wasn't too hard to show, using the comparison test, that the series of sine of n over n squared in absolute value converges. But now you have to ask, well, now what? The question was not whether the series of sine of n over n squared in absolute value converges or diverges. It was about the series of sine of n over n squared without the absolute value. Well, the question now is, if we know the series of the absolute value of the terms converges, can we say that the series of the terms without the absolute value also converges? And surprisingly, the answer is yes. If a series of terms in absolute value converges, automatically a series of the exact same terms without the absolute value also converges. And this we will prove in our next video, and this will be called the absolute convergence test. And this is just a result. If you sum terms of a sequence in absolute value and obtain a convergent series, automatically you can drop the absolute value on the terms you are summing, and this series also converges. And this result is called the absolute convergence test. And again, we will prove this in our next video.